I'm Alessio Ferri. I'm a developer. I've been at ThoughtWorks for about a couple of years now. I work in the London office, and today I'm with...
With Tom Colgrave. I'm a developer as well. I've been with ThoughtWorks for about 14 years or so now. It'll be 14 years in about 9 days or so, which is a different story. I work within one of our service lines where we try and build new services to take to clients. So looking forward to talking to you about this today. Thanks for joining us. I'll kick off. So today we'd like to take you on a bit of a journey through, as Chris said, a couple of different technologies, ranging from the very old to the very new. But what we want you to take away today is the idea that legacy modernization, and in particular mainframe modernization, doesn't have to be this huge, massive undertaking that is only available through kind of waterfall techniques, but we can get it done. We can all approach it as something that will achieve it in sort of months as opposed to years. So we're going to take you through a bit of a step into mainframe land, not too much, don't worry, I won't bore you all, and then talk about seams, like how do we tease apart the mainframe, before moving on to look at generative AI for how we then deliver the parts faster, and then conclude. So who has ever interacted with or done anything to do with mainframes? Show of hands? Cool. Okay. Cool. All right. Good. As expected, I think. I think it goes to show the sort of the level of knowledge and people out there who can still kind of do this technology is relatively limited. So I guess what's interesting about them? What makes them the most sort of hardcore of legacy? They have about a 70-year history, and I think the most interesting thing about this for me is, IBM has maintained backward compatibility with, I think, almost all generations of code that's ever been written for mainframes. So when you look at a mainframe system, you could be dealing with code that was written 40, 50, 60 years ago in whatever language was around that point, and it still will run today. And so that means you see a whole range of approaches to technology of that time. It's gone through like 5, 10 different teams of people who've looked at that. And I think Tricia was sharing earlier about how many lines of code per dev per day get written. I did a quick calculation about the client we're going to discuss today, who had about 25 million lines of code written in COBOL. I think that came out at something like 7,400 developer years worth of effort had gone into the system. So you can kind of see how the size and complexity of these things really goes into it. And so I guess just going back to that point about sort of modernization of these systems, a classical kind of modernization might look something like this, right? We do a whole load of development, and then at some point at the end, we get it into production, hopefully. And so you don't get any payoff until the end. But obviously there's challenges to this, right? You end up with, when things are going wrong or going off course, it's often too late and too expensive to course correct. And so these projects just get canned, get cancelled, thrown away, and nothing happens to them. Another challenge with mainframe in particular is the kind of availability of SMEs who can help you understand the system. As we've seen, maybe 2 or 3 people put their hand up in the audience. You may have seen some COBOL. Finding those people who still know the system in the company is actually very challenging. And then obviously trying to find new people who you can bring in to help you understand the system is also a challenge as well. There's no one really around. Well, there's fewer and fewer people these days who actually know it, who can help you with that too. And so I guess we wanted to take you through a bit of a journey today with a sort of banking and financial services information provider client where we tried to take a different approach, and we centered that around kind of early risk reduction. So how can we pay down some of the technical risks of these huge original monoliths? They are the original monoliths, and take an early and incremental delivery over Big Bang, so that we can try and achieve a curve that looks a bit more like this, so we get some early value and be able to turn that mainframe off hopefully a bit earlier as well. But the talk will cover slicing the mainframe up into smaller, or that legacy up into smaller, more manageable parts, and then speeding up the delivery of those parts, which is what I'll hand over to Alessio for. Over to you.
So I saw like a couple of hands when we talked about mainframes before, and I guess for the next part of the talk, we first need to open up these mainframes to see what's inside them so we can understand what we're going to be talking about. So at first, when I approached mainframes, this is what I understood about them. Like, they were just a big box. Really, I didn't know what was inside. It just felt very weird, very obscure. And also, I could only see stuff from its perimeter, really, like what you can see from the horizon, I guess, of this mainframe. But then you open it up with expert guidance, right? Because I couldn't do it by myself. And you understand that there are, in mainframes, it's typical to have like online workloads and batch workloads. Online are all these user-driven interactions with the mainframe. Think of them as like API calls or even interactions through green screens on mainframe, where you can like enter data and execute program logic. And in the batch world, instead, you like schedule things which run either at like time schedules or when specific things occur, right? And you got like these concepts of Kix transactions, so API-driven calls or possibly these screens that execute stuff, execute this single unit of work that will perform some kind of outcome on the mainframe. You got COBOL programs, but you can have more. Like COBOL is probably the least complex. Like there's Rex assembler, like there's a whole bunch of things that make it even more complex. But effectively, that's where you hold the business logic of the system that you're dealing with. You got relational databases. You got vSAM, which is some kind of like file-based storage system. Again, you've got in the batch world also those COBOL programs with JCL, which stands for Job Control Language. It's effectively like a way to configure how your jobs and what they need to do in a very simplified way. And you got files, and these files are like what we're used to deal with. They contain data, and they usually get exchanged in multiple places, especially in the batch world, where effectively you got programs after programs, kind of like modifying that data and then passing it over to the next job. Now, after I came to that conclusion, well, we came to that conclusion, I started comparing it with like other distributed systems. Are they really that different? The answer is yes, like mainframes are centralized. But once you look at these boxes, like what's inside of them, and then you compare it with like probably another distributed architecture, it won't be that different. Yes, the way it runs is different, but actually it didn't feel that obscure anymore. Like at least in my head, I felt like I could understand them, I could map them, I could work on them, right?
Yeah, thanks. So after that lovely kind of conceptual view, I guess, what does it actually look like when you crack open the box, right? Like, it's a much more messy picture. I think I would probably claim that this is still a simplified view. But you arrive, you kind of like crack this open, you see inside there's thousands of Kix transactions running across multiple sort of regions and all these sorts of other concepts that kind of add complexity to the situation. And you have to try and work out how to begin working out where to even start. And so I guess there's a number of different ways you can do that. Some of the ways that we do it would be to kind of map out data flows or look at kind of how APIs interact with everything, maybe map the applications or the capabilities that the mainframe is supporting. But I mean, some of the most useful views that we found were potentially, like a data flow view where we kind of trace some data coming into the system, it being operated on, and then kind of exiting out the other side, and then we produce many such of these diagrams to kind of map that process out. Another one might be kind of like, what are the transactional boundaries that particular APIs or applications have? So when they're touching kind of like databases or files, what are they doing? What's the process they're going through? What data actually gets mutated? And the reason for this is what we're really trying to find, I guess, is those entry points. So where does execution start? And that can give you a really good starting point for how to chop up kind of those processes, chop up the kind of the mainframe into smaller parts. I guess this leads us on to, I guess the other piece of value is actually in having the conversation with those SMEs. Like part of it is actually gaining that shared understanding about what's really happening in there to be able to have the conversation about where to break this up as well. And so I guess once you have that information, once you have that sort of catalogue of how all this stuff works, or enough of a catalogue to get started, then you might want to look at how we apply these themes. So not going to go into all of them today. We're going to pick out just a few that we thought were most interesting to kind of share in this audience. But effectively, you use these themes, or like we're saying that you use these themes to basically be able to break up that huge modernization program of work into constituent parts. So for instance, batch input is one of the ones we're going to cover first. That's how we might break apart a batch workflow that's coming with data coming into the mainframe. And then there's other ones like required side effect where we may have to crack open the mainframe and expose a piece of functionality we need to still call to keep the existing kind of system going so that we can do incremental delivery and release value early. And so I guess there's some characteristics that we look for a good seam. Typically, you want to look for something that is that you can almost do as much as possible external because of those constraints that you have where you have no one or fewer people available to actually make changes on the mainframe. You want to do as many changes off the mainframe as possible. It sounds obvious, but there's a lot of things that we considered during the client engagement that we were looking at, which we ended up discarding because it would have required far too many changes to actually make it happen. So the first one is batch input. So our client was like I said, a BFSI, banking financial services information kind of data aggregator. They captured a lot of data from the industry, from lots of different providers of information who actually tend to be their clients as well. They would bring all this information in, aggregate it, try and match it all up against particular individuals, and then provide useful products on top of that back to the industry itself. And so, one of the biggest things that they used to do was take in data from the outside world. They'd have people providing this data as files. Sometimes they'd be uploading it directly to the mainframe. Sometimes it'd be coming in through, in this case, a file server. And so this is kind of like probably the most simple seam that we can think to introduce, which is to introduce a seam around kind of like that file server. So if we have a piece of a file being provided by that file server, what we can do is we can, instead of just sending it one way, we can actually send it both to the existing kind of aggregation pipelines, but also send it to a new cloud version as well. So basically just bifurcate it or duplicate that flow of information and send it down two paths instead. Now that's really good because then we can begin building out our new applications in the cloud, begin like testing them, and in fact, on top of that, we can then also compare the output of those two aggregation pipelines as well. We can make sure that, for this client, it was very important that we kind of achieved almost the same results, almost exactly the same results as before, because of the importance of what the products were used for by the industry. And so we found it very important to be able to check and compare those two outputs to make sure that things were the same. And so obviously, once you've got that comfort, once you're happy with what's being produced there, then we can turn off the old kind of workflow, the old kind of processing pipeline. It's one of the simplest ones, and I think it's probably one of the most effective ones. It's one of those ones you can change it from the outside without having to go in and do anything particularly invasive within the mainframe. It's definitely one to look for to begin with. The next one I wanted to chat about was intercepting a pipeline handoff. Now, this one is slightly more invasive. What's involved here is, when you inside one of those workflows over there on the right that we showed, you may have a number of different steps, which is where we're passing files or messages or elements of data between different programs or processes. Maybe that's orchestrated by JCL, maybe that's orchestrated by something else entirely. And when you're trying to scope an increment of work that you want to deliver to production, you don't want to take in the entire world. So you want to be able to find hopefully as small as possible chunks of work to bring forwards. And so when I was showing you before that big picture about everything being entangled, you sometimes have to cut the boundary at a slightly more uncomfortable place within the mainframe. And so here we looked at introducing a seam that would basically capture the flat file that's coming out of there and pass it up into our cloud environment into a messaging system. A lot of the time in this environment, the data that was coming in could almost be treated as events. So like that flat file was basically just a huge list of kind of almost events that have happened. And so it fit the mold perfectly for passing up into, I think we used Kafka or AWS's kind of Kafka offering to kind of push that up there. We could then process that and store that into our new key value database, which was kind of the appropriate thing in this case. However, in this one we definitely needed to keep the existing kind of system working, and so one of the pieces that's important that a lot of our colleagues kind of talk about in the patterns of legacy displacement is about kind of transitional architecture. So that's the elements of architecture you have to put in that are like scaffolding to help you stand up something else up, and then once you're done, you take it back down again. But it's almost like temporary architectural pieces. In this case, we used replication. We put forwards to use replication to kind of bring the contents of that key value database back down into the vSAM data store that was there already. There's a few tools out there that can help you do this. Precisely is one of them. I think Click Data is the other one that was kind of in use there. And so using this, you can then basically build your new kind of like processing in the cloud and turn off something in the mainframe. The final one, probably the most complex one that I think we put forward at the client, was about splitting by data characteristic. So here we have, over on the right-hand side, a derivation pipeline. So we have on the left-hand side, a set of core pipelines that take in data from the outside world, aggregate it, and then store it in the first instance. But then from this, another set of downstream pipelines would pick up the outputs of that upstream pipeline and do some further work to work out a new entity on top of that. So in this case, they were trying to work out identities of, or trying to match data to identities out there in the world. And so there was a set of, this is a hugely complex area, and we didn't want to have to just do this all as one big bang, I suppose, and release the whole new derivation into the cloud. We wanted to break it down into smaller component parts and get some safety as we were going through to make sure that we were doing the right thing. And so what we did was having investigated the domain that was happening inside that derivation pipeline, we found that there was a series of sort of simple rules and slightly more complex rules. And basically, there's about, I can't remember, what was the number? Like 70 rules, I think, something like that. And so we looked at that and said, okay, well, let's break it down almost on a rule-by-rule basis, and we'll start by using a similar scheme to before, but basically pushing those flat file contents up into the cloud, and then beginning to process what we can. So we were able to begin implementing one of the simple rules, and then have that be pushed straight back into the database. But for the ones that we hadn't yet implemented, we would send the request back down to the existing kind of processing pipeline. So basically, it's almost a bit like a complex feature flag. We basically have a thing that's deciding whether we fork, which way down the fork we send those pieces of data and processing it. And so again, after time, the plan was to be able to then turn off the mainframe processing and have the processing run entirely in the cloud. And then again, using a piece of transitional architecture, we plan to replicate that the derived data back down from the cloud into the mainframe hosted database. So in that way, we can safely also kind of test out the new world whilst also keeping the old world working. So you're able to kind of check the outputs of what's going on up in the cloud whilst also maintaining what's happening in the mainframe. And so I guess bringing it all together, these are the sort of the set of themes that we looked at introducing. The ones I didn't cover, I can just very briefly. API access, I think folks would very easily recognize as a sort of a rewording of Strangler-Fig approach, where you can kind of wrap an API around the top and then send some requests some way to a new capability that you've delivered in the cloud versus others. Database readers was also one that the client was very kind of happy about using. That was where you, rather than having your readers use expensive resources on the mainframe, you replicate the data up to somewhere else and have them shift over to use that instead. That does come with some downsides that we talk about in the article about. You're then locked into the schema that was used in the database, the original database, so careful one to use. And I think I mentioned required side effects already. So, I guess we would say take a look at the article and try and see if any of these can be used in your mainframe kind of modernization efforts. Or if you ever run into one of these things, then can they be used there? But also they are applicable outside of mainframe as well.
Thank you, Tom. I guess, all right, so we now have a way of breaking down the mainframe into smaller parts. But the question is, do we still have legacy modernization to do nowadays? Right? Because if this was working just on its own, we wouldn't have anything to modernize, right? Everything would be already modernized. But the problem is that whilst seams make that challenge possible incrementally, these systems have been built over 70 years, 50 years, and rebuilding them takes a long time, right? And for many organizations, it's still not viable. Even though we can do things incrementally, the project might last for, 6, 7, 10 years. And why? That's because of those challenges. It's just the scale of the code base. We're talking about millions of lines of code. Like a medium-sized mainframe is 15 to 20 millions. Very few people know what's happening within the mainframe. We've got all those pieces, look at this one, for example, but where do we actually start from? Do we choose the smallest, the bigger? What is the sequence going to look like? In the market, there's a high shortage of people with skills on this specific tech stack, which makes these projects also more challenging. And what happens usually in organizations is that the technical expertise is outsourced. And so they bring people in that know COBOL really well. They're really good engineers, but they don't know the business context, right? Unless they stay there for a long time. So the answer is no. Seams are not, just on their own, they're not the solution to this legacy modernization problem. Other technologies also try to look at those challenges we looked at before. They addressed them, but they didn't solve them. And when we looked at those challenges, we thought, well, these are not just mainframe-specific things. Like, yes, maybe in mainframes the problems are accentuated, but if we could solve these challenges for mainframes, then we could apply them elsewhere and get those benefits for other legacy systems as well, right? Not just mainframes. And with the advent of GenAI, I guess, we were all amazed by the outputs that it could produce, and we thought, well, maybe it's worth giving this a try again and see if we could address some of those challenges at least. Even just alleviating them could ultimately bring loads of benefits for organizations that dare to embark on this journey. And so in the past year and a half, we ended up building a code discovery and intelligence tool for thought workers that work with clients that have to effectively deal in their daily job with complex legacy systems. It's not just to modernize, because what we are looking at right now is to explain the code, is understanding that code. Now, it can be used in modernization journeys, but it could also be used when, for example, I don't know, we've got to deal with a mainframe. We don't want to modernize it, but we still want to understand what's going on inside. And so the way it works, briefly, is we can visualize code bases on nice graph views. We can browse the documentation, which usually it lacks, like there's not that many documentation available for legacy systems. In this case, all the documentation is generated by LLMs, supplied with documentation if it's already there. And additionally, there's also a chat interface, so people can actually chat to it as if they were talking to a human that knows stuff about that code base. We ended up building in this year and a half parsers using ASTs that would break the code up into multiple chunks. We would use those chunks then to create a knowledge graph, and ultimately this knowledge graph would then fuel the LLM using RAG to get these chunks out and explain the code back to the user. It sounds rather it is complex, but we didn't start from here. Actually, we went through a journey of multiple iterations, and we want to walk you through that journey. So the first thing, very simple, we thought, okay, let's put a UI in front of GPT and let's try to find the best prompts that we can do that can extract the knowledge that we want to get from a piece of code that we're trying to analyze. So we pass in 100 lines of code. We have some prompt engineering in place that effectively passes the code to GPT, to a GenAI large language model. And through that prompt, with all the guidance that we've provided in the prompt, we get some information back. This was really cool when we did that because, well, I personally don't have any expertise on COBOL or any of those languages. I could understand what was happening in the code. I could just take 100 lines of code, 1,000 lines of code from there, paste it in there, get it explained. Yes, maybe a few details here and there weren't correct, but I could really understand what was going on. And maybe through supplementing that with actually looking at the code, I could fill in the pieces. It was still limited, though, because could you really do that for 15 million lines of code? Like, could you really take a snippet every time and explain it? So it worked, but it wasn't really addressing all of the other challenges that we had. And so we looked into RAG, Retrieval Augmented Generation, where it's very popular, by the way, in the world of GenAI. And the whole concept is about effectively the LLM doesn't have knowledge about your private data. And so you pass together with whatever prompt it is that you want to ask the LLM, you also pass the context. Imagine as if, I don't know, we talked to someone and said, oh, by the way, this is my organizational context, and I need to do that. What would you do? And because it's got that context, it can provide you an answer. And so we tried that, and we effectively chunked the code that we were dealing with. We put it in a vector database, and then do all of the plumbing to get the vector database to talk to GPT and get answers back from the questions that we were asking. This was different because we could actually interact with it without looking at code. Like, we could actually start to interact with the code base by asking questions. So we didn't have to actually get those 100 lines of code and put them there. We could ask questions and get something back. Which is, if you think about it, the more natural way of kind of like thinking about complex systems. You want to first understand the abstract level, which you typically look for in SMEs, and then you drill down into the details. But it was a limited solution, as in we needed self-descriptive code. to be able to search for the right things. We needed highly cohesive code because of a technical constraint in large language models, which is the fact that they have a limited context window. So you can't just pass whatever you want to them. You have to actually be very mindful about what it is that you pass to them and the quality of the context that you're supplying them with. And so we needed cohesive code because we needed, when we chunked the code into smaller pieces, if the code was cohesive, then we could effectively assume that whenever it pulled the documents back from this database, it would have all of the data required to answer that question. And we started to see those other challenges addressed, or we weren't like, they're still a bit blurry just because we weren't that happy about, like we still wanted to do another iteration to see better results for those things. And so we thought, well, there's intrinsically in code bases, so RAG works really well for unstructured data. But code is not unstructured. Like code has to follow a specific grammar. And so we thought, can we leverage that structure, the dependencies that we can have across files, across entities in the code, and build all of that onto a graph so that when we ask a question of the chatbot, it's able to pull back those documents as normal RAG would do. But in addition to that, once it finds the points in the graph through that vector database, then it can expand that context by providing something that, from a code perspective, is highly related to that node that we just pulled in. This meant that because we were leveraging the structure of the code base, we could leverage that structure from higher level of abstractions. Which meant that we weren't just searching on code directly, but we could also search on documentation generated by the LLM as it was traversing that structure. And so we could ask higher level questions that needed effectively knowledge from multiple different disparate places in the graph, and we could put all of that together in one place for the LLM to have access to when we asked questions. So yeah, we could do multi-index retrieval, so we could search on code, we could search documentation and provide all of that to the LLM. But there were some trade-offs in here, which was effectively we needed to pre-analyze the entire code base to understand what it was doing. Now, this is our last iteration. You remember the slide before, ASD, graph, and LLMs, and RAG. This is our last one where we try to address the scale of the code base. And before I said that we depended on highly cohesive code and self-descriptive code. What we're trying to do here is we're breaking down files even further and using ASTs to effectively extract from the code the logical parts that have to actually stay together. So we'll see an example later, but in simple terms, like how it maps in my head is imagine you've got a file with like two things one thing that calls another procedure in COBOL, but that second procedure is at the bottom of the file. If you just chunked the file, like, I don't know, at specific character sizes, you would miss that second bit from the first chunk, right? And so the idea of the ASTs is that we can break even further the code base and actually bring together those elements that would otherwise be far apart from each other. I'm not saying, sorry, previous slide. I'm not saying we've really solved the problem for context windows or we solved the problem for the scale of the code base, but ASTs are a really good way of breaking down the problem, breaking down the code to much smaller units. And depending on the code base you're dealing with, you can decide where you want to break that. Whether you want to keep if conditions together or you want to maybe, I don't know, take procedures by procedures.
Cool, thank you. So just to, thanks, so just to go into a little bit more detail about how this is actually working under the hood. Hopefully this is going to sort of round out kind of like the path that we've been on so far and sort of explain the detail about how we're actually using the technology under the hood. So at a high level, this kind of co-concise solution that we built is broken down to almost sort of three kind of stages, or three kind of components, right? We have this analysis pipeline. That's all about building up kind of like that graph and the descriptions and explanations about what's going on in the code. We have then storage in Neo4j, and then a web app that surfaces kind of the information, but also provides some chat capabilities at the top of that. We've switched to Java over here because I think probably based on the answers from the audience, thankfully people probably understand Java a bit better, or Java-like languages a bit better than COBOL, so I'm glad we switched towards that. But effectively, we're just going to quickly walk through exactly what's happening in each stage, and yeah, hopefully give some explanations. So as Alessio said, one of the biggest sort of steps forwards we've taken recently in this is using AST. So AST stands for Abstract Syntax Trees. We use parsers like Antler and other kind of other tools out there to basically produce a representation of kind of the sequence of execution, or the kind of the structure, sorry, of the code base or of a particular file. And so that's super important. Like having that in hand, as Alessio said, allows us to kind of be able to navigate contextually within the code when we're kind of operating on a piece of information. On top of that, we then add in not just the structure. We have access not only just to the structure of the code. So structure being a class is composed of a series of methods, and there's some variable declarations in there. But we can also ascertain that those methods are then calling methods on other classes. So you can actually then have a behavioral view of the code as well. And this we then store into the graph, and putting it in the graph makes it more accessible at a large scale. We need to have something persistent that's accessible to users even when we don't have it running on a laptop, right? So have to put it somewhere that means that they can access that. And so what happens next? Well, this is the kind of the bit that was the difference between sort of version 2 and version 3 of the approach. In version 2, we were just doing retrieval augmented generation over the code. In this version, we then use the graph and LLMs to be able to enrich that graph with explanations about what the code is doing at various points. So at the class level, at the method level, and actually you can then build it up to the package and even repository level. And so that comprehension will traverse in multiple ways. It does it structurally. So you have a method inside a class inside a package, but also it can use the fact that at this point in this method, we're calling this other method. Well, let's find out what the description of what that method is doing and use it when we're describing the class that we're actually in at the moment. So this is what's been able to kind of add a lot more richness and I guess clarity and correctness to kind of the graph that we have there. And so using both those traversals, we're then able to add those descriptions, and we then how do we then actually use it, right? I said before we have this kind of web app over on the right-hand side. One of the ways that we found, I think Alessio showed some screenshots earlier on in the presentation. We have like visualizations that allow us to navigate the knowledge graph in useful ways. And we also have the ability to ask questions and answers, or ask questions and get answers as if we're talking to an SME. But how do you actually make that available? Well, in Neo4j, we've been using this technique, this library called Graph Data Science. Graph Data Science is super, super helpful. I mean, if you've not played around with Neo4j, I would highly recommend playing around with Neo4j, but especially this library comes with a bunch of algorithms kind of pre-baked into it for doing kind of graph data science, but also it comes with a vector data store that you can then use to index a lot of your kind of information that you store in the graph. And so this is how we actually wire up our chat interface into the graph, is by using that to by vectorizing the question, by vectorizing the question we get from the user. We then find nodes that are related to that, expand outwards from there, grab those all up, find the relevant ones, and pass that all to the LLM to give it the best chance at answering the question within the context window that we've got, within those limitations that we've got. So that kind of is how we've brought it all together at the moment, and that's the kind of current state of it. So I mean, I guess like some successes and sort of some drawbacks, I guess, that we've had. We have worked with a client where we've managed to, they were taking kind of a manual approach to reverse engineering to get the requirements out of there. They were taking about 6 weeks of effort to get through 10,000 lines of code. We managed to chop off about 4 weeks of that to take it down to 2 weeks. And given they've got about 15 million lines of code, we think that's pretty scales up pretty nicely. We've been able to produce documentation, but also ingest documentation to improve the descriptions we're getting out of there. So it's almost like a virtuous cycle of documentation production there. And we've also been able to, as Alessio said, like be able to abstract at different levels to be able to answer questions as if you're kind of like a relatively new person saying, what even does this kind of code base does? Where is this thing implemented? All the way down to tell me how this COBOL method is, or the COBOL section is doing what it's doing. However, downsides, right? does require a bit of expensive upfront analysis. I think you could argue, I think we do argue, that if you compare that to the effort and the cost that goes in from a person sitting there and doing it, it's still a smaller number, but there can be some sticker shock when you get the cloud bill at the end, I'm sure. And it's not a silver bullet. Like, we took some missteps along the way that we probably won't go into as much detail about, but with a bit of over-enthusiastic LLM usage, where we tried to get it to do stuff that actually ASTs are much, much better at. And there's also this kind of trade-off, I think we're finding, between client-specific enhancements versus things that are generic. So one client we produced a lot of static documentation beyond what we normally would, and we have to sort of trade off whether we bring that back into the kind of core solution or not. And I guess just some future ideas, like we're planning to extend the use of the knowledge graph to then actually be able to, tying it back to the first half of the talk, how do we then find the seams in that code base? So can we use that, and this is a representation of kind of like some of our early attempts to do this, can we find areas in which we can then split the code base looking just at the graph, either statically or even asking the LLM or working with the LLM to see if there's some way to do it as well. So stay tuned for a bit more on that. I think I'm handing over to Alessio now to close out.
Thanks. So today we talked about two tools that we put and store in our legacy modernization toolbox. We think these are really important, but there's more to be considered. Like, these two won't be the only ones you would use on a legacy modernization. For example, on our specific experience with that client we were talking about before, testing and test data is also a challenge, especially because you've got these legacy systems that have been running for long and people are comfortable with what's happening, but the moment you change something, everyone is scared. And so testing, the test data, capturing all of these edge cases that people have built for, but do you actually have the data that can test for those edge cases? And so how can you also think about, for example, outcome monitoring? Tom before was showing the seams where we want to compare, like, over time, how the new system is behaving for what we effectively bifurcated and rebuilt. There's going to be a lot of scaffolding that will need to be built, and so a lot of platform thinking and platform engineering also needs to be thought about and accounted for early on, so that you can actually keep up pace of delivery for these modernization programs. And specifically dual run and transition architecture, so the scaffolding and every technical aspect that will enable teams to easily leverage those seams and make it almost like a commodity so that they can actually deliver fast. So what I guess we would really love for you to take away from this talk is that out of the toolbox, we think that Seams and GenAI are the keystones of the tools we have. And the reason for that is because without these two, we feel like a lot of organizations wouldn't even start their modernization journey, because it's just not effective. It just costs too much. So we use Seams to break the elephant into multiple chewable bites. And now it's almost lunch. But we use GenAI then, once we have these bites, to speed up the overall delivery of the program. And we think that these tools, this technology, whilst we've seen before in other talks that it's still not perfect when it comes to generating code, it's really like the explanations it can get on code is really useful. And we think that this can ultimately put legacy modernization or provide this as an option to many more organizations, so it won't be in the hands of the few. Thank you.